In this video, I want to have a look at the limiting sum of a geometric series. Now to do this, I want to start having a look at a sum. Let's say it has a first term of, say, 12. And I want to have a look at what happens when we sum terms. So let's have a look at when our common ratio is greater than 1. So for example, let's call it a ratio of 2. Then our terms, our sequence, would be 12, 24, 48, and so on. So we're doubling it each time. And when we add those together to make it a series, as we go towards infinity, as we add more and more terms, our numbers are getting exponentially bigger. So our sum is just going to take off towards infinity. Let's have a look instead at if our common ratio was less than 1. So let's say our common ratio is a half. So we'd start off with 12, then our next term would be 6, and 3, and 1.5, and it would keep getting smaller and smaller and smaller. So when we add them together, eventually we're going to be adding terms that are that close to 0, they're pretty much insignificant. So when that happens, when our common ratio is less than 1, then we're going to have a limiting sum because it's going to sort of flatten out as if there's an asymptote. It's going to approach a particular value. Now that example is only looking when we have positive numbers. The way it actually works is if the absolute value of r is greater than 1, then it won't have a limiting sum. But if the absolute value of r is less than 1, then it will. So that means that when r is between -1 and 1. So just to write that a bit neater, if the absolute value is less than 1, then the geometric series will converge. So it's going to get smaller and smaller and smaller, so that when we're adding those terms together of the sequence to make a series, it's going to be adding an insignificant amount, so it will converge. If r is less than -1 or greater than 1, then it will not converge. So the formula we had when we were adding n terms of a geometric series was this here. Now if we have a look at when we're adding more and more and more terms, so when our n is approaching infinity, we want to have a look at what happens to this sum. So as n approaches infinity, our r to the power of n, remember we're only looking at when the absolute value of r is less than 1. So we've got a small number and we're timesing it to a really, really, really big power, or pushing it to a really, really, really big power. This term here is going to approach 0. So that means that when we have this, if we've got our sum of infinity, so our sum of all of our terms, infinitely many terms, we're going to have a outside of 0 minus 1 over r minus 1. So that would give us minus a over r minus 1, or we could rewrite that as a over 1 minus r. So this is our limiting sum, and just again, it only works if our absolute value of our common ratio is less than 1. So it is written on your formula sheet as this as well. All right, so our first example asks us to determine whether the following geometric series will have a limiting sum. And then it says, if it does, we want to actually find what that limiting sum is. So for part A, we need to find our common ratio. So our ratio would be 6 over 18, which would simplify it to a third. And we know that that is less than 1. So because the absolute value of r is less than 1, then yes, it will have a limiting sum. So because it does have a limiting sum, then we can find it. So the sum to infinity is going to be a, which is our first term, so 18, over 1 minus r, and our r was 1/3. And then if we pop all of that in our calculator, we'll end up with 27. So the limiting sum is 27. If we add infinitely many terms, that 27 is what our sum is going to approach. All right, for question B, again, we need to start by finding our common ratio. So our common ratio would be minus 1/6 over 1/9, which would simplify to minus 1.5. If it's less than minus 1, or if it's greater than 1, then it will not have a limiting sum. Our second example tells us that a geometric series has a limiting sum of 5 and a first term of 3, and it asks us to find the common ratio. So we know that our formula is the limiting sum is a over 1 minus r. So we can put in what we know. So we're going to have 5 is equal to 3 over 1 minus r. And then we just need to solve this equation for r. So we're going to have 5 outside of 1 minus r is equal to 3, which means that 5 minus 5r is equal to 3. If I subtract 5 from both sides, I'd have minus 5r is equal to minus 2. And if I divide by minus 5, I'll end up with 2/5 as my common ratio. Our last example tells us that the series x plus x over 4 plus x over 16 and so on has a limiting sum of 7 over 8. And we're asked to find the value of x. So to do that, again, we know that our formula is a over 1 minus r. Now we need to figure out what terms we have. So we know that the limiting sum is 7 over 8. We know that our first term is x. And to find our common ratio, we're going to do t2 over t1. So we'd have x over 4 divided by x, which would just give us a quarter. So we're going to have 1 minus a quarter. So if I simplify down that bit, I'd have 7 over 8 equals x over 3/4. And then to get x on its own, I'm going to multiply. So I'd have x is equal to 7 over 8 times 3 over 4, which would end up giving me 21 over 32 as my first term in that series. So that's having a look at problems that involve the limiting sum of geometric series.